Hi and welcome again. We had kind of a short introduction to shaft design because of technology, and now I'm going to continue this introduction. So we've ended up in the previous segment talking about generally about how do you support shafts, and we mentioned that you need to carry axial loads and react those on the surrounding structure, and also not only that the axial loads, but you have to be able to support loading as a result of torque, because torque is needed to transmit the power. In addition, we have to transmit the torque, we have to use either gears or pulleys or similar devices, and in such a case there's going to be always a transverse force that must be also reacted at support points. So it becomes like a kind of a global design issue that must consider all of these cases in addition to the assembly, ease of assembly and disassembly. So let's look at continue looking at this here, in which we look at the shaft layout. So if you look at the axial issue, so the axial layout issue, it's if you here for figure A, we have gears and we need to put a shaft axially. So the way to do it is that we have to make the shaft of different sizes, so you can see it's stepping, and we have to make shoulders, and the shoulders are at locate the gear. So the word location is important because that's high precision to make the shoulders where the gears would sit, and the gears themselves will have to be prevented from axial motion, and therefore there must be some other devices here that will allow not to move axially. In addition to this, there would be support points, and the support points, as you can see here, are generally taken up by bearings, like roller bearings, for example. Another example is when you have fans or pulleys, and in this case you can use set screws, and the set screws kind of locate the pulleys in their respective axial location for high precision, for preventing excessive deflection of the shaft assembly. Now the other point is that when the shaft is to transmit some axial force, for example, the axial force has to be taken up by the structure. So the structure is right here. So how do you take up the axial force on the structure? The system that is used is that at one location only, usually, that you have one bearing, and the bearing, you can see this is cylindrical bearings right there, and you can design machine the surfaces so that you have mechanical interlocking around the bearing. So this is mechanically interlocked, and then the shaft is tapered so that it can sit on the bearings, and then the bearings are mechanically interlocked here, and everything should be assembled with tolerances. So the word tolerances is important to prevent binding of the shaft, so it can actually freely rotate. So you can, if you browse through the next few figures, you can see a variety of devices. For example, here's the screws. They're used to attach the structure to allow transmission of adequate transmission of forces. You can see cylindrical bearings when you have a shaft and then it has a fan, for example. So these are all considerations that are taken into account when we design the shafts. The second element of this is the transmission of torque, and the transmission of torque is obtained by using a number of devices For instance, keys and splines and set screws are used to transmit torque, and sometimes we use either pins, or we can also use the idea of press or shrink fits to make sure that components or parts of the shaft will fit into each other. So these are possibilities that are used for the providing torque transmission. In addition, we have to consider the assembly and disassembly as an important element of the shaft system design. And as you can see here, that we have screws that attach. This is the structure around the shaft, and at the end the shaft is attached to roller bearings, and the shaft has a shoulder, and the shoulder now is obtained by machining, precise machining, so that you can have all the surfaces mating with one another. So when you design the system, you have to design for quick assembly and disassembly. Like you see in this case, there's a little gap here, and the gap is maintained with a spline, so that you can prevent binding, or you can allow for some temperature kind of expansion coefficient to take care of the elongation of the shaft. Now, when we do shaft design for stress, then we don't really look for every possible point in the shaft system. We determine critical locations, which are on the outer surface, where the moment is large, and when we have moment plus torque, and when we have stress concentrations. So that can usually be like a manual process to locate where you want to evaluate the stresses. Then when you evaluate the stresses, we have to consider, if you have a moment on the shaft, so you have a bending moment and the shaft is rotating, you will see that the bottom fibers undergo compression and the top will undergo tension. So the moment is usually associated with an alternating component of the stress. On the other hand, if you have a torque, the torque is fixed, and it translates into an average or a mean component of the stress that must be taken into account. And therefore, we usually have two types of stresses. One is the alternating due to the moment, MC over I, with the stress concentration factor, Kf. And if we happen to have a mean value of a moment, which doesn't occur very often, we can also find the mean stress. The same, we can apply the same idea to calculate the torque, and the torque induces a shear stress, alternating shear stress, with a stress concentration factor due to shear. Kfs is for shear. And similarly, we can compute the mean value of the applied torque. If we now think about it, we don't have square shafts that are rotating. Usually these are round shafts, and therefore the I and the J can be easily introduced, and the C would be D over 2 because it's on the outside, so that these equations here simplify into the equations that you can see in the bottom here, 7.3 and 7.4 for round shafts. Generally, we would have an alternating bending stress and a shear stress, and therefore we use the simplified form of the von Mises formula to give us the effective alternating stress. So sigma prime is effective, or von Mises, and plugging in the previous formulas for sigma alternating, tau alternating, we can obtain a relationship that includes the alternating moment and the alternating torque, and the shaft size, as you can see here, as well as the stress concentration factors. Same thing can go for the mean value of the von Mises stress. When we design now the shaft for stress, we can use the von Mises stress, and we substitute it into, for example, any of the failure equations, the criteria equations. For instance, the modified Goodman line gives us a factor of safety once we have the alternating over endurance and the mean over the ultimate. And here, this is designed for infinite life. Usually, we design the shaft for infinite life. So I'm going to leave it at this. Equation 7.7 and 7.8 are just basically substituting for sigma alternating and sigma mean the von Mises stress, and you can solve it backwards for the required diameter to satisfy a certain value of the safety factor and required for the design. So this we can, as you can see here, these equations that we described come exactly from what we've learned before, because we are able to compute the shear stress due to torsion and the bending stress due to a bending moment, and then we can combine them into von Mises and use them into modified Goodman. We could do the same exact idea using either Gerber or the ASME or any of the other equations that we have learned, and therefore that can be developed as you can see here in the equation 7.9 and 7.10 for the dE is distortion energy, which is von Mises related to Gerber, and you could do the same thing for dE Goodman, dE Gerber, etc. So these are just applications of what we've learned before, so don't get too concerned with the complexity of the equations, because they're basically substituting the values of the torsional shear stress and the bending stress, as well as the stress concentration factors that we've learned before. So all of this is basically what we have gone through it to determine shaft stresses. One of the critical ideas is that the mean value of the moment in shaft design and M mean and the alternating value of the torque in shaft design are usually equal to 0, unless it is very rare case that these are not 0. So that kind of simplifies the equations, the previous equations, when you substitute for the mean moment to be 0 and the alternating value of the torque to be 0, then the equations would simplify and we'll be able to compute the fatigue life easily from any one of the previous equations. In addition to fatigue, we also check for static failure, and the static failure summarized here. If we use Soderberg, then we don't need the Langer line to check for failure. If we don't use Soderberg, then Gerber and Goodman, we require a specific check for fatigue using the Langer line to make sure that on the first cycle we don't induce yielding of the shaft. So this is again something that we have discussed before. So in the following, what I would like to do to finalize this lecture is describe an example, and in this example we will go through a process of designing a shaft under the conditions of bending moment and torsion. So if you consider here we have a machine shaft, is the small diameter, lowercase d is 1.1 inch and capital D is 1.65, and we have a fillet radius of 0.11 inch. Now we have a bending moment of 1260 pound-inch, which will result in an alternating component of the stress, and we have steady torsion of 1100 pound force inch, which will result in a mean value of the shear stress. And we have a heat-treated steel shaft. It has ultimate strength 105, KSI, yield strength of 82 KSI, and we need a reliability goal of 0.99. So what we'd like to do, we want to find the factor of safety for design. And we want to determine the yielding also factor of safety. So fatigue, we want to design for fatigue, and we want to design it for yield. Two conditions here for this design. So we will start by looking at the process that we will describe here, is that we want to design it for an infinite life. So we have the ultimate strength of material. First, we want to find the endurance limit for the rotating beam, which is half of the ultimate if it is steel. And then we want to make corrections for the endurance limit for the practical fact that we have a shaft that has a specific size and a specific surface conditions and specific loading, for example, bending. So we have to apply the Marin factors to that. Now, in order for us to apply the Marin factors, we need to go back to the tables and use the Marin factors, and then we will set aside, then we'll be able to find the endurance limit, the corrected endurance limit. Next, we have to do the loading, and we get the bending, stress, and the torsion can induce shear. Not only that, but we have to find the stress concentration factors. Those usually we obtain from figures under static conditions. And then we have to use the notch sensitivity factor for fatigue to make corrections to these factors and derive the corresponding stress concentration factors in fatigue. So it's kind of a little bit long story, but we have learned it before, so we can go through it here. So as you see that I have, this is lowercase r over d, this is the fillet radius over lowercase d. Then with these two parameters, I'm able to go to figure A15.9 and get the stress concentration factor under static, and the same thing under shear. And now I can find the notch sensitivity factor for axial loading and the notch sensitivity factor for shear loading, and then make the corrections with the notch sensitivity factors to convert the static to fatigue, and I'm ready now to amplify the nominal loads with these two factors. Before I go there, I get the rotating beam endurance limit corrected for the surface finish, and corrected for the size, and the other factors, Marin factors of 1, and then we have a loading factor bending 0.8. So it knocked down from 52.5 to 29.3. So it's a big drop in the endurance limit that we will have to be careful in applying. Once we've now got the stress concentration factors and the corrected endurance limit, we are ready to go, because we can use the moment and the torque. This is alternating, this is mean, so both the mean and the alternating of the bending and the torsion respectively are 0, and therefore if I use the distortion energy to find the Goodman criterion, as we've seen one of the equations before, then I'm able to compute the fatigue safety factor, and it's here 1.63. So I can, as you can see, if I have a simple MATLAB program, or if I'm using my calculator, I'm able to program these previous equations and find the fatigue factor of safety if I'm considering the variety of options that we have, the 4 options, Soderberg, the ASME, and the Gerber, in addition to the modified Goodman. I have a variety of safety factors, and I'll choose the safest approach for fatigue design would be the ASME elliptic, for example, in here. So in addition to this, I need to guard against yield from the first cycle, and I can guard against yield by finding the equivalent stress alternating and the equivalent stress due to the mean value of the torque, and then I look at the application of the Goodman. This is a Goodman failure criteria. Still, it's a different way to find the fatigue safety factor. But for the first yield, I must find the maximum stress, and the maximum stress would be the maximum value of the von Mises stress. So this is max bending, and this is max torsion. And then I add the two of them together in the von Mises sense to produce the maximum von Mises stress of 18,220 psi. And since the yield strength is 82,000, then the factor of safety for yield is essentially 4.5. So now this is a complete example for just the initial shaft design where we have combined axial bending and torsional loading, and we have alternating and mean values in order for us to design the shaft for an infinite life. In the next lectures, we will go more into other aspects of shaft